Okay, let's look at the third video for current of electricity. Okay, so thermistors. Okay, they're just a resistor with a line through it. Now these are inverse to how a normal conductor varies its resistance with temperature. So, if you think about it, if I graph resistance versus temperature, okay, so as we increase temperature with one of these ones, we're actually going to reduce our resistance. So it's opposite the behavior. Power, okay, power is essentially the same, but we can use some terms we've known for electrical energy. So power is equal to work divided by time. Now we can use two definitions to create a new power formula. So work is VQ in terms of potential difference, and charge Q equals IT. Okay, so two defining formulas. Now, if we put the expression for work from the potential difference definition to the power equation, so power equals work over time, if we put into there our VQ, we will get VQ divided by time. Now we can substitute in IT for that Q, so then you'll get P equals VIT divided by T. T's removed, and you get P equals VI. The other way of thinking about it is Q divided by T is also equal to I. Using V equals IR and P equals VI, we can create two new equations. So if I grab P equals VI and substitute in for V, IR, because IR is equal to V. So let's put in there IR times I, and then you get P equals I squared R. Now that equation there is actually the heating equation. Okay, so if you're working out the heating effect of a current through a certain resistance of a wire, then you can work out the power, which is the heating. Let's look at this formula again. And let's rearrange and make this, let's get rid of, this time instead of getting rid of the V, let's get rid of the I. So what's I equal to? I is equal to V divided by R. So putting V over R in for I, you get V times V divided by R, and that gives you P equals V squared over R. You don't have to remember these formulas, but you should probably think about how they come about. Example, power line is carrying current of 200 amps before a transformer. The resistance of the wire is 0.15 ohms. Calculate the rate of energy loss in the wire. Okay, we've got resistance, we've got current, so you could use I squared R. Where it says rate here, well that's what power is. Power is equal to work divided by time. So anything divided by time is rate. If there's an exam question that asks for something per second and so on, then that's what you're looking for is the rate. After the transformer, the current is now 5 amps. What is the rate of energy loss now? Okay, essentially the same sort of thing. Okay. Yeah, so every device has a internal resistance that creates an EMF. Okay, you need current still needs to flow through a battery, and it's not a perfect conductor inside the battery. So if you have a cell, okay, when current flows through that cell, there's still some sort of resistance inside that cell, and generally we denote it with a small r. So here's an example of a circuit. We have an EMF, we have a resistance inside the cell, and we have a load resistance. Now, we should know from previous experience that the total voltage supplied to a circuit is equal to the total voltage removed from the circuit. So in this circuit, we're going to have an EMF in. Okay, so this is V in, Okay, and then we're going to have a potential difference across the cell resistance, and then there's also a potential difference across that load resistance. And all that depends on the current. Now, so V in should equal the sum of all the potential differences. So essentially what we're talking about here, the EMF is going to be equal to the sum of the potential differences across the two resistors, the load resistor and the internal resistance resistor. If we look at this part here, if we look at the simple circuit, so we've got internal resistance, got a load resistor, so a little r, big R, EMF, and we have a current I. Now if we decrease the size of that resistor, the total resistance in the circuit, remember for series it's just going to be R plus R, that will decrease, so the current must increase. Okay. Now the power given off by this one, or let's say work or anything like that, so in other words the voltage loss across that one is also going to decrease, so it's actually going to increase the voltage across that little resistor, and so more energy loss. Now you can treat these circuits just like a series circuit, and that's my recommendation, is how you treat these. Now another thing that's quite interesting is if we had just a D-cell battery, if you attach a wire from one end to the other, the actual battery itself gets very hot. The reason for that? Well, it's going to be a very high current because there's a very small resistance around there. Okay, and so that means there's going to be a large voltage across the internal resistance. Okay, and that means the thing will get very hot there because that's where all the energy is getting converted. And that's what this page here is talking about. Now in this first example here, you have a 9-volt battery, okay, connected to a short circuit, so there's a wire going around there. Now it says there's 8 volts measured between there and there. Okay, so that means we lose 8 volts around the circuit. Okay, we must have lost 1 volt in the circuit. Because we're measuring, let's say, 8 volts here, and we could be measuring then 0 volts there. So the difference is 8 volts around the circuit. Current is 5 amps. 5 amps is everywhere, so including through the cell. So that means in the internal resistance in the cell, we have a potential difference of 1 volt and a current of 5 amps going through that resistor. So using V equals IR, in this case R equals V over I, it will be equal to 1 over 5. And simplify. Second one there, what is the EMF of the battery in the following circuit? Okay, bit of circuitry stuff here. What's the total resistance there? I'll give you a bit of a clue. Okay, the 8 and the 4 are going to add together to make 12, and then you're going to do the parallel resistance. So remember, 1 over R equals 1 over R1 plus, and so on. Okay, let's do that in our head. So we're going to have 1 over 12 plus 1 over 4. So you're going to do, you got 3 over 12 then plus 1 over 12, so that makes 4 over 12. Inverse that is 12 over 4, and that equals 3. So a total there of 3 ohms. So to get 5 amps through the circuit, okay, we need to find the total resistance circuit. It's not just going to be 3 ohms, okay, it's going to be 13 ohms. Okay, so then to find the total voltage, it's just going to be IR, so it's just going to be 5 times 13. Hopefully that's right. And the next one is very similar, just a lot more, a similar sort of process. I'll let you think about that one. And here's the answers. As you can see, 65 volts is the same as 5 times 13. Okay, so we got there in the end, just slightly different way. This thing is interesting. Okay, so have a good read of that. This here is a good little demonstration of the voltage as the current goes around the circuit. So you get the rise because of the EMF, no change in the wire, hit the internal resistance, you lose some energy, wire no change, and then your load brings you down to zero. So that's a good little example.